So thanks everyone for coming to the reading group today. So we are very glad to be presenting our own work this time for TGB 2.0, a benchmark for learning on temporal knowledge graphs and heterogeneous graphs. So this will be a joint presentation between me and Julia, which we are both co-first author on this work. So there's question. Okay. Yeah. So I won't be going over too much of our own bio because we'll be giving the talk. But yeah. But you can find like information about us on the reading group website. Um. So I will get started on the presentation then, and feel free to jump in and ask questions or clarifications. Okay, so in this work, we want to tackle temporal knowledge graph and temporal heterogeneous graph. So before we go there, so here's the like our collaborators and the TGB 2.0 team. And thanks to everyone who contributed to this project. So I will start the talk by discussing the background of temporal graph learning, um, kind of giving a bit of introduction. Then I will talk about the like last year's paper of temporal graph benchmark. Then I will go into the multi-relational temporal graph, which is the focus of this project. Introduction. So we know that temporal graphs are ubiquitous. So we know that many of the relationships in the real world that actually change over time. So two concrete example here. So on the left, you have the Canadian Parliament voting networks. So the voting behavior between the politicians would change from year to year, but depending on the political dynamics. And you also have flight networks. So this example here is the flight network during 2020, which was actually like severely disrupted due to COVID-19 and so on. Um, so so when you model these networks as temporal graphs, um, the nodes and edges in these graphs can be added or deleted over time. And in addition, the feature of the graph can also change over time. And these models are called temporal graphs. So to be more concrete, in the literature, there's two main representation of temporal graphs. Um, and the first type is you represent temporal graph as a sequence of snapshots. This is more natural kind of representation that follows from static graph. And this is often called the discrete time dynamic graphs. And the second representation, which is um, considered to be more general, is the continuous time dynamic graph, where you represent the graph as a stream of events. Here, the timestamps can be very fine-grained, like second-wise and so on, and the edges can arrive at any time. So the main motivation for the line of work on temporal graph benchmark is that we realize that existing data sets are limited in size. So here's the example for the common temporal graph datasets in our 2022 paper, which we considered around 13 datasets, and we see that most of these datasets are relatively small in size, have less than 2 million edges, and less than 1 million nodes. So the motivation for the benchmark is to also include newer datasets that are larger in scale. So in terms of the motivation for the first TGB work that we built upon is the lack of realistic and large-scale data sets and the lack of standard evaluation similar to what OGB have done for temporal graph. And then lastly, we also see from the literature that the high performance of existing methods makes it really difficult to differentiate between them, which then hinders the progress in the field. So now I will briefly talk about temporal graph benchmark bracket 1.0, which is our last year's work. Um, so, so in this work, we construct a diverse set of data sets, um, and these are large scale and realistic data sets. And then you can load these data sets into the TGB data loaders, which then process them for your machine learning models, and you can insert your own models in the middle here. And we provide both link and node property prediction tasks. And the TGB package basically automatically handles the downloading and processing of data sets and provide them in different format that you might need for your method, like NumPy, PyTorch, and PyG. And also, we provide a standardized evaluation protocol that are reproducible and realistic. And lastly, you can follow the state of the art on the public and online leaderboard. And I think like recently there's quite a bit of change on the leaderboard. So if you're interested, you can go and check out the leaderboard to see the new state of the art. And we'll keep updating it as new methods are submitted. So yeah, so we see here in terms of the size, the TGB 1.0 datasets are much larger. And here's an overview of the datasets. But one thing to notice here, when we started the work, the scope was limited to standard temporal graph datasets, which means these are homogeneous temporal graphs where there's a single type of link and a single type of link. So that's the main focus for the first work. And at the end of that work, like when we presented last year, so we also received a lot of feedback on if we can add new data sets for temporal knowledge graph, for example. So here we would like to thank everyone for your feedback and support of TGB. And this motivates us to start working on the second version, which I will present today. And we plan to continue to update and improve the benchmark based on your suggestions. So here I will get into multi-relational temporal graphs. So what are multi-relational temporal graphs? So as the name suggests, these are temporal graphs that contains multiple types of relations. So here's one example temporal knowledge graph. So of the US. So on the left, you have a graph snapshot at November 2017. And on the right, you have June 2021. So you can see that in November 2017, Donald Trump was president of the United States, and he visits China. And then in June of 2021, Joe Biden was president, and he visits the UK. So you can see that the information and these knowledge are also changing over time. So such as presidency and so on. And we want to model these different relation types as well as how they evolve over time. So broadly, we call them multi-relational temporal graphs. And there's two main types that we consider in this work. So one is temporal knowledge graphs. So temporal knowledge graph is a set of quadruples where you have the subject and object, and as well as the relation type of the link and the timestamp. So some examples of temporal knowledge graph are knowledge bases and political event networks. And we also have temporal heterogeneous graphs. So these, when compared to temporal knowledge graph, these have additional like information about the node type. So for each node, you will specify which type of node it is. So here some examples are software networks, like you have the different GitHub history. You also have social networks and interaction networks. So the task here is that you want to make link prediction or temporal graph extrapolation to predict links that will happen in the future by leveraging the past information. And in terms of the limitation of existing work, so one major thing is the limited size of existing common benchmarks. So for standard temporal knowledge graph datasets, these are usually less than 2 million like edges and less than 1 million nodes. And that's also true for temporal heterogeneous graphs. So we want to address these challenges for multi-relational temporal graph in this work. So we want to help provide a standardized evaluation procedure. So in the past literature, there are inconsistencies in terms of the evaluation metrics, and also like mixing multi-step and single-step prediction settings, as well as using different versions of the same data set. And for temporal heterogeneous graph, the evaluation is limited to just using one random negative sample per positive edge, which can lead to over-optimistic performance. And also the dataset size, as we see, are limited. So now I will start to introduce temporal graph benchmark 2.0. So in TGB 2.0, if you are familiar with TGB, the setup and the code structure is exactly the same. We have also merged the code back into the main TGB repo. So when you install the software there, then you can have access to all these new data sets as well. So the workflow is the same. So you have the data sets and they are processed by data loaders, which here they will be processed like differently for knowledge graph or heterogeneous graph, and would provide you with the edge type information and the node type like information in the case of the heterogeneous graph. And then you can insert your own model there. And then you can then evaluate based on the TGB evaluator and then submit to the leaderboard. So we have added a total of 8 new data sets, including 4 temporal knowledge graph and 4 temporal heterogeneous graph data sets from 5 different domains. We also provide the same automatic data downloading and processing, and the data evaluator, as well as the public online leaderboard. So in terms of the size of the TGB 2.0 datasets, so here on the left, in the orange dots, are our new datasets for temporal knowledge graph. As you can see that all the new datasets are quite large, and the largest one are orders of magnitude larger in number of edges, nodes, and timestamps. And the size of the circle is the number of timestamps, for example. And on the right, you see the new temporal heterogeneous graph datasets, where the newer ones are also significantly larger than the existing datasets in terms of scale. And in the paper, how we represent these different type of temporal graphs is that we follow the common representation, where for temporal knowledge graph, they are commonly represented as a sequence of snapshots. That is because the time granularity of temporal knowledge graph is usually much coarser, so the knowledge doesn't change on a second-wise basis. So we usually have like yearly granularity or daily granularity, and then you also have for the temporal heterogeneous graph where it's represented as a stream of edges. So that's the same setup as in TGB 1.0. And the time granularity here is per second. So I'll quickly talk about the data sets. So here are the data set statistic of the new data sets. So for the temporal knowledge graph, we have domains from the knowledge bases and political event networks. And for the temporal heterogeneous graph, we have graphs from the software or like from GitHub, and then from social network, as well as like user and app interaction networks. And the largest data set that we have is the 53 million edges for the MyCat data set. And the 5.8 million for the number of users on the GitHub one. And there are some other statistic here. So like, for example, the inductive ratio. So that's the amount of test nodes that are inductive that you have not observed during training, which is quite high for the knowledge graphs in general. and still quite significant for the heterogeneous graph as well. And then we also have some other statistic, then you can check the details in the paper as well. And these data sets will be permanently maintained on the Digital Research Alliance of Canada. So when you download it, it will just be one URL and you can download. And we split all the data sets chronologically into training, validation, and test set in terms of like 70 and 15 and 15%. And the data sets are classified into small, medium, and large based on their computational cost. So for the temporal knowledge graph data sets, we have the smallest one, which is the TKGL Smallpedia. So this one basically contains Wikidata entries that have their IDs smaller than 1 million. And these would describe point in time like relationships, which is more like one-time events, or the relationships with durations, like this person is the citizen of this country for a period of time. And we also include, very interestingly, the static relations from the same set of Wikidata pages. So the hypothesis here is that you can leverage the static relations to boost the performance when you are trying to learn these temporal edges. And the duration is from the 1900 to 2024. So I won't go over all the details here, but I want to highlight that basically the Polycat and the ICWS are different political event networks. So these have like the edges about different political news and so on. And the Smallpedia and the Wikidata are from Wikipedia, and they are just different sizes and also spans different duration. And for the temporal heterogeneous graph data sets, so we have a similar case where we have the software data set, which is a smaller subset of the GitHub data that we look at the nodes with more activities with 10 edges, and then the duration is for the January of 2024. And then we have the other ones. So we have the forum, which is a subreddit interaction network. And we have the MyCat, which is the user and app interaction. And we have the largest GitHub dataset, which is containing more nodes and links. And here are some statistic on the number of edges over time. And we see that on the Wikipedia, as you get closer to the modern age, you have more knowledge, as we expect. And for the heterogeneous graph, it's usually quite stable over time. There are some peak in the variance, and these are likely due to one-time events and so on. And we also show some example of the relationship types and so on. And I will now hand the mic to Julia.
Thank you. I'm gonna share my screen.
Yeah.
Okay. Can you see it already? No. Okay, so I'm going to talk now about the experimental setup and about the experiments that we did. So we do temporal graph extrapolation. So we want to do link prediction for future time steps. For example, Kalia Copper is a member of which kind of sports team in a future time step. And we do single step prediction, so we always predict one step into the future. And as a metric, we use the so-called time-aware filtered MRR. So we rank the true target out of many negatives. And then there's a bit of a differentiation between the temporal knowledge graph evaluation and the temporal heterogeneous graph evaluation. Namely that for temporal knowledge graph evaluation, we predict in both directions. So we might predict the object or the subject. And in temporal heterogeneous graph evaluation, we always predict in one direction. Which is the reason is that this is what it's commonly done. And then there's another thing that we focus on, which is the number of negative edges. This is also different for temporal knowledge graphs and temporal heterogeneous graphs. And we selected this based on a trade-off between evaluation completeness and evaluation efficiency. So for like complete evaluation, you would want to rank the true target versus all potential nodes in your graph. However, for the very, very large knowledge graphs or heterogeneous graphs that we have, this is not really feasible because it's simply too many. And this is why for the temporal knowledge graph datasets, for the smaller datasets, we did this one versus all evaluation, where we compute a rank among all potential nodes in the knowledge graphs. And then for the large knowledge graph, for the Wikidata knowledge graphs, we sample Q negatives to compute our MRR. And we sample the negatives based on the edge type. So we only sample among the nodes in the graph that have the same or had previously the same edge type or were connected to the same relation as a true edge. And then for the temporal heterogeneous graphs, it's a bit easier for us because we do know the node types of each node. So we can sample the negatives only with the same node type as the true destination. And then also for the experimental setup, we do 5 runs. And for each run, we report the average and the standard deviation. And in this case, we select limits. We do have 40 gigabyte GPU limit, memory limit, and a 7 days time limit. And if an experiment does not finish in that time or is out of memory, then we consider it as out of time or out of memory, respectively. And now I want to talk a bit about the experimental results, first for the knowledge graph and then for the heterogeneous graphs. For the temporal knowledge graph experiments, we selected these methods, REGCN and CEN, which have like a sequence of knowledge graph snapshots. Then they have a GCN and put a sequential neural network model on top with different kind of tricks. And then T-logic, which learns temporal logic rules. And in addition to that, we have 2 deterministic heuristic baselines. One is called the recurrency baseline, which predicts recurrent triples. And then the edge bank, which also predicts recurrent edge, but it does not integrate the edge type, so the relation information. And what do you see? There's a big table with results for the 4 temporal knowledge graph datasets and the different methods. We report the validation and test scores, and we report the MRR. So higher is better. The bold values are the highest ones, the underline are the second highest ones. Out of time is OOT and out of memory is OOM. And we see some things. For example, we see that this baseline, this recurrency baseline, is competitive across many or most data sets. For example, it has the highest results here and also second highest here and here. This suggests potential areas for improvement for other methods because it's just a simple baseline. And also it shows that it's somewhat important to include simple baselines when you do comparisons. We also see that the edge bank heuristic, which is originally designed for homogeneous temporal graphs, exhibits somewhat low performances compared to the other methods. So we do see that it is important, or it is quite a big of a benefit if we do include this relational information that we have given in the temporal knowledge graphs. However, also to be seen here is on a large Wikidata dataset, EdgeBank is the only method that finishes. This shows that it's feasible to predict something for Wikidata, but also it shows that there is quite a bit of a need for more scalable methods, or the existing methods should be made more scalable. And then we also see that if we compare the MRRs across datasets, we see that for the Smallpedia and the Wikidata, which are the datasets where you have relations like works at, lives in, so relations that recur, so where the things recur more often across time steps, for them we have in general higher MRRs as compared to the datasets which are characterized by more single events happening. And then we also have some more detailed results. We report them for all the data sets in our paper. Here we just show it for now for the Polycat data set. Here you see the MRR across selected relations and for 3 different methods. And then the color also indicates the recurrency degree of those triples. So how often do they recur over time? Higher is more often. And what we see is that across the different relations, we have a somewhat consistent performance. So it's always in the same range of the MRR. This suggests that the relations are somewhat similarly easy or hard to predict. And we also see that we do not have one method which is the best across all relations. But here, for example, the baseline method is better, and here the CN method is better. So there's quite some difference. And then now, on the contrary, when you look at the small PDI data set, this distribution looks rather different. We see that we have some relations which have a very high MR values, and also the color distribution is quite different. So we see that we have some relations which recur more often, which have a high recurrency degree. And for them, we in general also observe higher MRRs, which is also intuitive because if things happen over and over again, they are also easier to predict. And also we see this high variation among relations. Yeah. And now when we look at the temporal heterogeneous experiments, here we use slightly different methods. On one hand, we use the STHNN, which features a heterogeneous link encoder where you have a type encoding, you have a time encoding, and then also you have the sequential representations that are used in the encoding. And then we use the widely used TGN method, which has been developed for single relational temporal graph learning. And we also have an extension of TGN edge type, which is modified to also incorporate the edge type information as edge feature. And then also we compare again to these two deterministic heuristic baselines. And here we have the same kind of table, now with the THG data sets. Same meaning, same metrics. And what do we see here? First, we see that SDHNN achieves by far the highest performance on the THGS software data set. So we see that this method, which was designed specifically for THG, can gain quite significant performance gain. However, we also see that it's the least scalable and it's unable to scale to all the other data sets. So it's out of memory for all the other data sets. We also see that the edge bank has pretty competitive performance with that of TGN, while being scalable to the large data sets. So again, it's important to evaluate against simple baselines. And we also see that for these data sets, we have quite a significant challenge for the methods on the larger data sets. And then we also see that when you compare TGN and TGN edge type, we see quite some significant improvement when TGN uses the edge type data. So there is, again, quite some potential to leverage this multi-relational information that we have in the temporal heterogeneous graphs. So in summary, what did we find? Both the TKG and the THG methods struggle with large-scale data sets, often resulting in either too long runtime or exceeding the memory limit. So scalability is an important future direction. And we also see that the heuristic methods that we tested against achieve competitive results on both data sets. So it is important to include them, and there is hopefully room for improvement for current methods. And now to wrap it up, we introduced TGB 2.0, which is a novel benchmark for evaluation on multi-relational temporal graphs. We have in total 8 new data sets. They are quite much larger than existing ones, and they are diverse in statistics and in dataset domains. And we did some experiments where we found that methods struggle with the large data sets and that the heuristic methods have competitive results on both kind of data sets. And while in future work, we would be interested in working on additional evaluation settings. We would be interested in working on more domains like biological networks, citation networks. It would be cool to benchmark both continuous and discrete methods. There was, for example, the recent work of UTG towards a unified view of snapshot and event-based models for temporal graphs from Andy and the team for some new ideas. And then also we would be interested in other types of temporal graphs like text attributed graphs, spatiotemporal graphs, and so on and so on. And if you have any feedback on what else to include, or if you're interested in contributing, Here's Andy's email address, so feel free to contact us or also on Slack. And here we have QR codes to GitHub website paper. And we will be very happy if you try TGB 2.0 and if you let us know any feedback that you have. And yeah, that's it from my side. And I think we have some questions in the chat, but also feel free to just ask them. I'm going to check the chat.
Hey, it's me.
And sorry. Yeah, okay.
Can you hear me?
Yes.
Yes.
Oh, sure. Thanks. Fantastic work. Thank you. And I'm trying to, read as much as possible and trying to understand all the prior work and your current work. And it's quite overwhelming, but I'm slowly trying to assimilate the knowledge which you have put in the papers. Thanks for that.
Thanks for that feedback.
Yeah, it's hard in these times where the landscape is very fast moving and it's very difficult to focus on get up to speed on something. So for the SDHN efforts, right? Like I see that it's very hard to scale. You mentioned you're constantly hitting out of memory. So I'm sure you would have tried, but I just asked in the chat whether you try to do the garbage collection more frequently, or probably even after every epoch or whatever. Have you tried that?
So I think it should be clean like it like working in terms of batches of edges. So it should be clean like after each batch. But the main issue is more about kind of how much entities like that it needs to track over time. And I think like in terms of the code detail, I think pharma will know more on the implementation side. But I think it's more about like how many things that you need to maintain in the memory, and then at a certain scale, then it starts to break. But yeah.
I see. I see. So you're storing the nodes as well as their associated edges in memory
As
for
well as
each.
some node type information and potentially node feature and so on.
Okay, on a per batch basis, right?
Well, not only per batch, because you also need to remember past information, right? So some of these models need to keep track of stacks of past information or past like neighborhood and so on.
I see. Uh-huh. Okay. Okay. I'll go look into the code, see what's going on there. Perhaps I can maybe if I can help. I don't know. Um, and I
It
have
would for
another
sure be
question.
appreciated if you find something.
Mm,
Yeah, so like definitely some optimization can be done. So these models are like when they are published, they are usually not tested on the largest data sets. So when you stretch their limit, then things start to break. But I
mm,
think the main focus of the work is more to benchmark them and see where the limit hits. And then I think there's needs to be a lot more optimization that happens in the field, like in general in terms of the implementation and so on. Um, and yeah, so that's definitely like something to look into.
right. Right. Totally. Another thing is I see in most of your experiments, you're focused more on link prediction.
Mhm.
Since this is all we are talking about dynamic graphs here, in many cases, um, it would be helpful to you and decide what this node is. Probably for the past for the past 3 months, this particular node has been behaving like this, and all of a sudden, this morning, this node is behaving completely differently. So you could um, so you could do two things, right? Like, in terms of just if you focus on the nodes, probably you could have something like, first understand the node itself uh, for the past 3 months. How is this node behaving? Probably the node could have a legitimate behavior of like three different ways it could be behaving. And we can just have a baselining that And in 3 months, we know that this node behaves in 3 different ways, and all these 3 different ways is legitimate. And suddenly this morning, if it behaves in a weird way, which doesn't fall into these 3 different categories, then it's something to look into, but at least for the baselining effort, we can focus more on node feature changes over a period of time. Have you thought about that? What are your efforts there?
Yeah, so in terms of this question, I think you are referring to anomaly detection in a sense, kind of when you have unexpected like behavior that happen. And the issue with that is, so the issue is more about how do you get these labels to begin with? So how do you know that how to categorize this behavior as such and that behavior as that? And what kind of ground truth like label you need to use it for evaluation? These are usually pretty hard to come by and well defined. So that will be one limitation. So like in this work, we focus on the link level tasks. It's mostly because that's the most common task in those 2 line of work, and there's a lot more benchmark methods on those. But I think that's definitely possible to add node level tasks and even graph level tasks in the future. Yeah.
Yeah.
There's
I,
yeah, go ahead.
Yeah, I see your point that for such tasks you may need some labels, but some effort could be done without labels itself. You can just label them into categories like 0, 1, 2, because they differ by so much. And then and then finally, if something very much changes, both in terms of nodes features as well as its topological activities, difference in the topology, right? For that particular node, then probably something could be, some alert could be raised. I'll think about that and I'll maybe discuss with you later on, discuss with the group.
Yeah.
But it's all good. Thank you so much. Appreciate that. Yeah.
Thank you for the questions and the discussion. So feel free to do follow-up discussion on the Slack and so on.
Fantastic. Sure.
So there's also more questions. So I will just quickly like answer questions from the chat. And thanks for listening, everyone. So for the from George, I don't know how to pronounce your name correctly. So I apologize in advance. So your question, do you want to ask like yourself?
Okay, so my doubt is I don't get if the data sets of the benchmark is just about graphs that incorporate new edges or new nodes, or if they have graphs where these edges and node features they evolve through time. So, for example, we can do graph signal processing in some sense that there is a time series intrinsic in the edges and the nodes. So
Yeah.
a node features in a given t equals 1 is different from t equals 3 for the same node. I don't know if you approach this in the data set.
So for the data set that we provide, we mostly focus on the changing topology, so the graph structure itself. But what you refer to is more, from my understanding, is more like a spatial temporal graph where you have relatively fixed graph structure, but the signal on your nodes are changing. So that would be a different kind of type of temporal graph that we don't currently support, but that could definitely be an interesting future work to add. Yeah.
Okay, thank you, Zen.
So maybe to add on top of this, to make it clear that these data sets, they do not come with certain types of node features. So we just have the node ID and we have the relation type, but no node features that change over time. Andy has said it, but to make it clear.
Yeah. So if there's any feature, it's pretty much static. It's not going to be changing. There are some cases that definitely does change, but I think that's more in the spatial temporal graph side, as I mentioned. Yeah.
Great, thank you, Andy. Thank you.
Sorry if I'm jumping in, but I was like to ask this a really similar question. And first of all, sorry, thank you a lot for the presentation, and sorry for jumping in. But similar for like these questions, I was more thinking on, I don't know, face-to-face social interaction in which this you have both the changing in the topology. Suppose, I don't know, people that talk, their topology change over time, but then if you model their feelings or how they feel about the conversation, these change over time. So I do agree with you that finding this data is not easy at all. And of course, there is, in this case of social face-to-face interaction, there is the problem of collecting this kind of data. But I do believe that as a future work, as soon as we found this data, adding them to TGB will be a really good point. So just to add this.
Yeah. So I think so just to answer your question in two aspects. So one is in terms of like face-to-face contact network. So actually there are those data sets, but as you would expect, these would be private. So we actually, in our group, we have done research on disease modeling with human contact networks. And of course, the data sets, except for the a few smaller public ones that's been well documented, in general, it's something that is highly important, but almost always going to be private because that's privacy issues. But these networks are very interesting as well. And I think main application would be you can extract the graph structure and see how the interaction changes the spread of disease, or in a different sense. So kind of to your second point, is that you also have different kind of sentiments across temporal graphs. So like spreading like misinformation on social networks or these kind of things. So these, in a sense, you could get some data sets for that, but of course it's also a large effort to actually go and monitor that, and then you also run into like the copyright issues and so on, and privacy. So, but I think that's another. But these two are very similar. They are all kind of diffusion process on top of temporal graph topology, which have very clear applications, but of course it's very difficult to draw any theoretical conclusion or something like that. So, yeah.
Yeah. Thank you for the answer. Yeah, I mean, I agree with you that getting this data, they are private. So, but it will be super interesting.
Yes, if such sources do come up, I think it'll be very interesting to add. Yeah, totally agree.
Thank you.
Thank you. Yeah, so thank you for the engaged discussions, and feel free to follow up with more questions on Slack or message me there and so on, or by email. And thanks for coming to the presentation, and we will share the slides afterwards as well. Yeah, thanks everyone.
Thank you.
Thank you so much.
Have a great day.